Ever wondered what space-time really is? Imagine this. Space-time is like a giant four-dimensional grid that combines space and time into one unified framework. Unlike a literal sheet, space-time is a mathematical construct that describes the fabric of our universe. Think of it as a grid, where each point represents a specific location in both space and time. This grid helps us understand how gravity works. Now let's dive into the curvature of space-time. According to Einstein's general relativity, massive objects like planets, stars, and black holes curve the space-time around them. Picture space-time as a flexible fabric. When you place a heavy ball on it, the fabric bends, creating a dent. These dents represent the gravitational influence of the mass, so the heavier the object, the deeper the dent, and the more it affects other objects around it. But remember, there isn't an actual physical sheet beneath space-time. This sheet metaphor simply helps us visualize how mass warps the fabric of space-time. When we say masses leave dents, we mean that their presence causes space-time to curve around them, and objects move along these curved paths. Let's break it down further. Gravity isn't a force in the traditional sense, like a rope pulling objects together. Instead, it arises from the curvature of space-time caused by mass. Objects move along the curved paths, or geodesics, determined by this geometry. Finally, at very short distances, space-time involves gravitons, quantum particles associated with gravity. Gravitons collectively create the curvature of space-time, much like photons form electric and magnetic fields. Imagine if we could bend the cosmic fabric to travel faster than light. Sounds like science fiction, right? Well, modern theoretical physics offers some intriguing possibilities. First, let's delve into the concept of manipulating space-time. Albert Einstein's groundbreaking theory of general relativity introduced us to space-time, a unified fabric combining space and time. This fabric isn't a literal sheet, but a mathematical construct that massive objects curve, affecting how matter and light move. But what if we could create wrinkles in this fabric? Enter gravitational waves, ripples in space-time. Detected by experiments like LIGO and Virgo, these waves confirm that space-time can indeed ripple. Imagine space-time as a calm pond. Massive events like merging black holes create ripples, gravitational waves that travel through the fabric. Now let's explore a captivating idea inspired by science fiction: the warp drive. In 1994, Mexican physicist Miguel Alcubierre proposed a hypothetical way to travel faster than light without violating the laws of physics. Inspired by Star Trek, the warp drive involves creating a bubble of distorted space-time around a spacecraft. Inside this bubble, the space behind the ship expands while the space ahead contracts. The ship itself doesn't move, rather, space-time does the work, essentially allowing the spacecraft to surf on a cosmic wave. However, Alcubierre's model faces significant challenges like the need for negative energy and exotic matter and issues with stability. Despite these hurdles, the concept has inspired countless studies and continues to fuel our imagination about the future of space travel. Next, let's consider wormholes, another theoretical shortcut in space-time. Often referred to as Einstein-Rosen bridges, wormholes could potentially connect distant points in space, much like folding a piece of paper to bring two points together. These cosmic shortcuts could, in theory, link galaxies and allow rapid travel across vast distances. While we have no experimental evidence supporting the existence of wormholes, they remain a tantalizing possibility within the framework of general relativity. Stabilizing a wormhole would likely require exotic matter with negative energy, adding another layer of complexity to this fascinating idea. Finally, let's touch on the mind-bending concept of time travel and the paradoxes it presents. Mathematically, space-time can adapt in ways that might avoid these paradoxes. Classical dynamics and general relativity even hint at the possibility of paradox-free time travel. Some researchers manipulate entangled particles to simulate backward time travel, suggesting that quantum mechanics might hold the key to unlocking this enigma. Now that we understand how massive objects curve space-time, let's explore how this curvature affects light. The curvature of space-time profoundly influences the behavior of light in several fascinating ways. First, let's talk about the paths light takes. According to Einstein's theory of general relativity, massive objects like stars, planets, and black holes curve the fabric of space-time around them. When light travels near these massive objects, it follows the curved paths dictated by this geometry. This phenomenon is known as gravitational lensing. Light doesn't bend because gravity directly affects it. Rather, it bends because space-time itself is curved. Next, let's consider time dilation and its effect on light. Time dilation occurs due to the varying gravitational field strength. Clocks in stronger gravitational fields run slower than those in weaker fields. Light experiences time dilation as well. When it passes through a gravitational field, its perceived frequency and energy change. This effect is called gravitational redshift. Near massive objects, light appears redder or lower in energy than when observed far from them. Moreover, light always travels at the maximum speed allowed by the laws of physics. The speed of light denoted as c. From our frame of reference, time effectively stands still for light. This means that light doesn't experience time dilation as we do. However, it still follows the curved paths in space-time due to the mass-induced curvature. The bending of starlight around massive objects is a fascinating consequence of Einstein's theory of general relativity. To illustrate this, let's talk about gravitational lensing. When light from a distant star passes near a massive object like a galaxy or black hole, the object's gravity bends the path of the light. This phenomenon acts like a cosmic magnifying glass, allowing us to observe objects that would otherwise be too far away to see directly. One of the most famous confirmations of this effect occurred in 1919. During a total solar eclipse, two independent teams measured the positions of stars near the sun's limb. They confirmed that starlight was indeed bent by the sun's gravity, as predicted by Einstein's theory. This result marked the triumph of general relativity over Newtonian physics, demonstrating that massive objects curve space-time and affect the paths of light rays. Finally, consider the principle of relativity. Inside an elevator or any closed system, you cannot determine your velocity relative to the outside world without external reference points. Similarly, light traveling near massive objects follows curved paths due to the space-time curvature caused by those masses. The bending of starlight is a direct consequence of this geometry. Now that we've delved into how curved space-time affects light, let's venture into an even more intriguing territory. How would manipulating space-time affect our understanding of causality? The manipulation of space-time, whether through wormholes, warp drives, or other exotic means, has profound implications for our understanding of causality. Let's explore this fascinating interplay. First, consider causality and light cones. In space-time diagrams, we depict causality using light cones. These cones represent the paths of light rays. The past light cone includes all events that could influence a given event. The future light cone includes all events that could be influenced by it. Causality relies on the strict ordering of events within these cones. Next, let's think about warp drives and time travel. A warp drive, if feasible, could create a bubble of distorted space-time. Within this bubble, the ship experiences faster than light travel. However, the warp drive's impact on causality is uncertain. Could it violate the chronological order of events? If we could warp space-time to reach distant stars quickly, would we inadvertently alter the past or disrupt causality? Then there are wormholes and temporal loops. Wormholes connect distant regions of space-time. Entering one end might lead to emerging at the other end in a different time or place. The famous grandfather paradox arises. Could you travel back in time and prevent your own existence? Wormholes challenge our intuitive understanding of cause and effect. Consider also closed time-like curves, or CTCs. Some solutions to Einstein's equations allow for closed time-like curves, paths that loop back in time. If CTCs exist, causal loops could occur. Imagine receiving a message from your future self, acting on it, and causing the future self to send the message. This raises questions about free will, determinism, and self-consistency. Finally, quantum mechanics and retrocausality. Quantum entanglement hints at non-local connections between particles. Could information flow backward in time? Some theories propose retrocausality, where future events influence past ones. Manipulating space-time might reveal deeper connections between quantum phenomena and causality.